Welcome back. Today we are going to consider this second example of the principal agent model. The second example is not example 2, it's example 1.5. The reason is it's really similar to the first example, example 1. I make only just a few changes to produce this example 1.5. So the description of the model is really similar to example 1. So the agent's reservation payoff is 0 as before, but the agent's action space is now continuous. Previously in example 1, the action space was discrete, so the action was that could be taken was just 0 or 1 or 2. So the action could be only 0 unit of effort or 1 unit of effort or 2 units of effort. But now you can choose, the agent can choose any number between 0 and 2. So which means we are going to we can use calculus if we want. And the output space, the revenue space, is still binary, but I use different notations. In the previous example, the high revenue was 10 and low revenue was 5. But instead, here I'm going to use these more general terms. So the high revenue is denoted by this XH, and low revenue is denoted by XL. And the revenue or the output X is XH with probability A over 2. This is same as before. And the principal's payoff is the profit itself, X minus W, as before. And the agent's payoff is W minus C times A squared. So in the previous example, there was no this constant C, but now I just added this constant C just to add a little bit of flavor into the model. So the agent's payoff is it becomes slightly more complicated, but not very much. And we are going to assume that xh minus xl over 4c is smaller than 2c. We are going to see why we need this assumption soon. Okay, so this is the second example that we are going to consider in this discussion. So as I said before, now the action space is continuous. We can use calculus, we can differentiate the objective function if we want, which is a big advantage. Even though at first glance, now the agent has more options, more choices, more effort level, so that that the agent can take. So maybe the problem becomes slightly more complicated, but as a matter of fact, as we will see very soon, actually the problem becomes simpler to analyze. So let's see. So here is the agent's payoff. So agent's payoff, or the agent's objective function, is expected wage minus the effort cost. So expected wage is expected value of W of X given A minus the effort cost is C times A squared. And the expected wage can be spelled out like this. So with probability 1 minus A over 2, the wage is W of XL. So with probability 1 minus A over 2, the revenue, the realized revenue is XL. In that case, the wage will be W of XL. And similarly, with probability A over 2, the revenue is realized as XH, and in that case, the wage is W of XH. And we can rearrange the term to produce the third line. So we just take out the W of XL, because that's just given number from the agent's point of view. So we can regard it as a constant, right? So So for the agents maximization problem, WXL is just given number. It's just we can take it as just constant, okay? And we can just focus on the agent's choice variable. In this case, the agent's choice variable is A, right? The effort level. So the coefficient of A is W of XH minus W of XL over 2. So this is the coefficient of A. Because it looks a little bit chunky, so let's introduce a new notation. So delta W is the difference between WH minus WL. So WH minus WL is delta W. Okay, so then at the last line you can see a very simple, nice a quadratic function of A. So it's a quadratic function. It's you can just differentiate, and the coefficient of the higher term, higher order term. So the A squared is negative, which means this quadratic function is a single peaked concave function. So you can differentiate this with respect to A, then you can have you can derive the first order condition. So the first order condition is the condition of for the maximization. So it looks like this. So the on the left hand side you put the first derivative of the objective function, and on the right hand side you put 0, right? So what that means is the first derivative, which is the slope of the tangent line of this objective function, is 0 when this objective function is maximized. So that's the first order condition, and you can solve that equation for A. Then you derive this optimal effort, which is A star, which is delta W over 4C. So this is very simple, nice. So we like it. And you can try to understand what that means, and it's easy to understand. So the optimal effort level increases as delta W increases. So what is delta W? Delta W is the additional wage when the output is high. So WL, or W of XL, is the baseline wage. So that's the wage that you get no matter what. So you get you get W of XL even if the output is very low. And if the output is high, then you get additional wage. That's delta W. That's the bonus, right? So delta W is the size of the bonus. So if the size of bonus increases, then your effort level will increase. That's one observation. The second observation. So, and if C increases, what is C? C is the coefficient of the of A squared, and C times A squared is the effort cost. So C increases if the what that means is the effort cost increases. So C is not exactly the marginal cost, but is related to the marginal cost. Just the meaning is very similar to marginal cost. Let's just call it marginal cost for a moment. And then the interpretation is easier to understand. So the if C, the marginal cost increases, then the additional cost, so additional effort, becomes more costly. So you don't want to put too much effort, right? So that's why we see the coefficient C at the denominator. So as C increases, the optimal effort level decreases. Okay, So that's the meaning of this expression. So we derive this optimal effort, and uh, just go back to the big picture. So we consider the last stage first. So what we just considered, what was the agent's utility maximization problem at the very last stage, at stage 3. And in stage 2, the agent decides whether to accept the offer or not. And in stage 1, the principal or the employer makes a contract and give it to the agent, uh, and if the agent takes it, then the contract will be enforced later. So uh, so this is the last stage of the game, and now we are going to move backward or upward toward the earlier stage, the first stage. So in the first stage, the principal is making an offer. So when the principal is making an offer, the principal deliberately choose the best wage schedule or the best contract to maximize the profit, the expected profit. So the principal's objective function is the expected profit, expected value of x minus w. And we have these two constraints, right, as before. So the first constraint is called IR constraint, right, short for individual rationality constraint. And the second constraint is called IC constraint, short for incentive compatibility constraint. So the first constraint makes sure that the agent accepts the offer, right? So the left-hand side of the inequality is the expected utility of the agent when taking this offer. There is a typo. At the effort cost, there must be C in front of A squared. Just write C in front of A squared. So that's the expected utility of the agent, and the right-hand side 0 is the outside option value or reservation payoff of the agent. So if expected value of wage minus A squared or C times A squared is larger than 0, that means the agent is better off by accepting the offer. So that's participation constraint. And the second constraint is the IC constraint. This is the constraint, this is the equation that we just derived, right? So the effort level or the optimal effort level is delta W over 4C. So given the wage schedule, the best response of the agent or the optimal effort, optimal response of the agent is given by this equation. So optimal effort is delta W over 4C. I forgot to mention this, but I forgot to mentioning this. The optimal effort is a function of delta W. It's not a function of any other W. What I mean is, it's not a function of WL, for example. So, only the difference matter, right? So the baseline wage doesn't matter. So the baseline wage is WL, and WL does not appear in this expression. So the optimal effort is determined by the difference in wage. So the difference in wage is the size of the incentive. Okay, so we have these two constraints, IR constraint and IC constraint, and as before, you can show that the IR constraint must be binding. So the IR constraint can be written like this. So the in the equation at the bottom, so the very last the left hand side is the expected utility of the agent, right? So WL plus delta W over 2 times A minus C times A squared. So this is the expected value of the agent. You can check by going back to the previous slide. So this is the expected utility of the agent, and it can be rewritten like WL plus delta W squared over 16C by plugging this delta W over 4C into A, right? So what we just did is we put the optimal effort uh, in A. So we impose the IC constraint into the IR constraint to derive this expression WL plus delta W squared over 16C. So we just eliminated A. So it's just function of W, right? So this is the expected utility of the agent, and that must be 0. So that's what the binding IR constraint means. So if the IR constraint is binding, then expected utility of the agent must be 0, and this is exactly it. Okay, so binding IR constraint looks like this, and let's move on. So the expected profit of the principal can be written like this. So expected profit is like this. So with probability 1 minus A over 2, the realized revenue is XL. And in that case, the profit will be XL minus WL, or W of XL. And with probability A over 2, the realized profit will be XH. The realized revenue will be XH. In that case, the profit will be XH minus WH. And we can rearrange the terms, and we can rewrite the expression like this. So XL minus W of XL plus delta X minus delta W. Here, delta X is, as before, XH minus XL. So the difference in X is written as delta X. And similarly, delta W, as we saw, delta W is the difference in wage. So that WH minus WL is written as delta W. So by doing this, we can express this this expected profit as a function of A, right? And the next step is, as you can see, we impose the IC constraint. So we put delta W over 4C into the place of A. So we replace A by delta W over 4C. So we impose IC constraint to derive this, and the next step is we impose the IR constraint, the binding IR constraint. So as you can see, we impose the binding IR constraint in the way to replace WL, or W of XL, by minus delta W squared over 16C. And then you just calculate the difference between delta W squared over 16C minus delta W squared over 8C, and then we derive the expression at the bottom. Okay, so expected utility, expected profit of the principal can be written like this. And to derive this, we use both the IR constraint and the IC constraint, which means we already imposed these two constraints. Now we can just maximize. Sorry. What? Yeah. Sorry. Yeah. Okay. So this is the principal's problem. So the original problem looked like this. So you maximize the expected profit subject to the IR constraint and IC constraint, and it can be rewritten as this. So you maximize this I don't know, this objective function. It looks slightly more complicated. but we don't have constraint anymore. So we transformed this constraint optimization problem into a unconstrained optimization problem. So you just maximize this objective function without thinking about any other constraint. Okay, so and here the choice variable is delta w, because we don't have any other w. So in the original problem we were supposed to maximize the objective function by choosing the right w. Here the w was a function, right? So w was w of xl and w of xh. So w was a function. Now in the transformed problem, the choice variable is a scalar variable, which is just denoted by this delta w. Okay, and it's unconstrained optimization problem, so it's very easy. And as you can see, this objective function is a quadratic function of delta w. So you just differentiate this quadratic function with respect to delta w, then you will get very simple first order condition, and if you solve it, then you derive this condition. So the optimal wage schedule must satisfy this delta w equals delta x. So the difference in wage must be the same with difference in revenue. Okay, so this is one equation that we have to use to write down the solution, and the solution looks like this. So the optimal wage is a strategy. Optimal wage is strategy. What I mean by that is the optimal wage is a function of w's, or sorry, mathematically the optimal effort is function of wage, and in game theory term, the optimal effort is a strategy. By strategy, what I mean is a complete action plan. So it's a complete description of the optimal effort given any contingency. So any realization, any possible w, the optimal effort level is described by this function. Okay, so you can put any number in this WL and WH for any W, any numbers. You can this function show that what the optimal effort is. Okay, so that's what I mean by a strategy. A strategy is a complete action plan, and this function shows a complete action plan of the agent. Okay, and the optimal WL star is given by this minus delta x squared over 16c. In previous slide, we saw that the binding IR constraint requires that WL equals minus delta W squared over 16c, but what we just derived is delta W must be same with delta X, so instead of delta W, we put delta X, and WH star is WL plus delta X, and this is what we just derived, right? So delta H minus delta L must be same with delta X, XH minus XL, and you can rewrite that expression in this way. So as you can see, A is function of W, and W's are functions of X's, and these X's are just given numbers, right? Like, in example 1, they were 5 or 10, right? So the low revenue was 5 and high revenue was 10. So these are just given numbers. So these are the numbers that we can make assumption of. So this is the solution of the model. This is the description of the equilibrium. So given this expression, you can put some numbers in xl and xh and c, and c we can check what happens in equilibrium, right? For example, if delta x increases, what happens? If delta x increases, WL will decrease, right? And WH, what will happen in WH? WH will increase for a while and then later will decrease. And what happens to A star? If delta x increases, A star will also increase. So the optimal effort level will increase. Okay, so that's what we are going to see when delta x increases. Okay, so what happens if C increases? If C increases, the optimal effort will decrease, of course, and also WL, the optimal baseline wage, will increase, right? If C increases, then the denominator of this expression, so the 16C, so the 16C increases, and then the absolute value of WL will decrease, but this WL is a negative number, so WL itself will increase because it's a negative number. So you may wonder, is it possible to give a negative wage? So according to this expression, the WL is negative, right? So the baseline wage is negative. Is it possible? My answer is yes and no. It is possible, yes, because maybe if you do something bad, if you make a harm to the employer, then you have to compensate the loss to the employer, right? That can be expressed as a negative wage. So negative wage is possible, it's theoretically it's possible, and you can imagine situations where the workers pay back to the employer when things are really bad. And another answer was no, so I said also no, and that was what I mean by that was this. So we don't have to take this negative wage literally. Okay, so in this example, we assume that the reservation payoff is 0, but the reservation payoff, the 0 reservation payoff was just one way to simplify the model. So maybe in reality the reservation payoff is not 0. Then the reservation payoff will appear in the expression of WL. So if the reservation payoff is high enough, then WL will be high enough, then we don't have to worry about negative wage. Okay, so that's the second answer. So first answer was, yeah, it is theoretically possible to give a negative wage, and the second answer is that if we consider a positive reservation payoff for the agent, then this WL will be positive. Okay, so this is the equilibrium that we just characterized for the example 1.5, and it looks simpler and more elegant than the equilibrium that we derived for example 1. So then why do we care? Why did we consider example 1 in the first place? The reason is we considered example 1 because I want you to think about this situation carefully. So if I just show you this differentiation and this standardized way to solve game theoretic model, then you just do it almost automatically without thinking. But if you see this discrete action space and the discrete options, then you have to think about which one is better. You have to think about the narrative. You have to think about what's going on in the model one by one, and that's what I wanted to you to think about. Okay, but eventually, these two models are very similar. In example one, we had multiple equilibria, which means that infinitely many wage schedule could be an equilibrium, right? But here we can pin down the exact number for WL and WH, and the reason is simply because we are considering a continuous action space. Uh, okay, there is nothing really deep economics in there, so don't worry too much about this multiplicity of equilibria in example 1, and you can understand the entire economics uh, of example 1 using this example 1.5 by looking at this example 1.5. Okay, and just few more remarks for the solution. So what we found was this. So delta W must be same with delta X, and this is very peculiar feature of this model. So we have name for this kind of contract. So this kind of contract is called selling the firm contract. The reason is this: the changes in the revenue is entirely reflected to the wage. That implies that the principal does not take any risk. The principal does not take any responsibility, while the agent who actually does the work, who actually puts effort and make the business working, takes the entire risk. So it's like the principal is selling the business to the agent, and the agent becomes the new owner of the firm and puts effort and takes the entire responsibility and risk as the new owner. So it's like selling the firm to the agent. Okay, so this kind of contract is optimal if the agent is risk neutral. So how do you know that the agent is risk neutral? The agent is risk neutral because we assumed a linear utility for the agent. So agent utility was linear in wage, right? So as wage increases, the agent's utility increases linearly. So that means the agent is risk neutral. The same is true for the principal, but what's more important is the agent risk attitude. Okay, so here we haven't talked about the tension between insurance and incentive, and one reason is we haven't we haven't figured out the optimal the first best contract. So we haven't compared this the solution that we just derived to the first best case, and the second reason is there is no tension between insurance and incentive in this model. This is more fundamental reason, and there is no tension between insurance and incentive in this model because we were considering risk neutral players. So the principal was risk neutral and the agent was risk neutral. So they don't care about risk at all. So we don't have to think about insurance at all. So of course there is no tension between insurance and incentive because nobody cares about insurance. So the only thing they cared was the incentive, and it turned out that the principal gave full incentive to the agent. By full incentive, I mean the maximum incentive, which is expressed in the in the equation on the slide. So delta W is exactly same as delta X. That means any change in revenue is reflected entirely to the wage. That means the agent takes entire risk, and also in that case the agent's incentive to work is maximized. Okay, that's what I mean by full incentive. So because nobody cares about nobody cares about risk, especially the agent doesn't care about risk. So it's optimal to give full incentive to the agent. Uh, Such a contract is called selling the firm contract. Okay, so to understand the tension between insurance and incentive, we have to consider risk averse agent. So, what is this risk aversion? So, if the agent utility function is concave, as you can see on the left, then this agent is risk averse. In contrast, if the agent's utility function is linear, as you can see on the right, then this agent is risk neutral. And in example 2, we are going to consider an agent with concave utility function, and that's the topic that we are going to discuss next time. Okay, thanks. Bye.